folks, we're here at the end of things. So let's try and put this together as best we can, and we'll just factor these polynomials. So as I look at 6a, I notice that there's 4 terms, so I'm kind of thinking I might need to factor by grouping. That would be something I'd be suspicious of. And I don't see a GCF, right? There's nothing common to each of these in that, like, 20 and 5 have a number in common, 12 and 3 do, but collectively 25, 12, and 3 do not have anything in common, so there's not a GCF. I'm going to go ahead and factor by grouping. And let's see what we get here. If I group first 2 and second 2, and I'm just going to try this grouping. I don't know if that's correct. If it is, great, and if not, I'll try first and third, second and fourth. And then if that doesn't work, I'll try first and fourth, second and third. I just go until I can't anymore. All right, so let's see. If I think about 20 and negative 5m, I could see a 5 common. So that would be 4 minus m. And I'm going to take the negative, because if I think about what's in common, or what's common to negative 12n and positive 3mn, I'm going to take out the negative 3n. And when I take out the negative 3n from the negative 12, I'm going to have 4. When I take out negative 3n from positive 3mn, I'm going to have minus m, which is great now that I look at it, because that back factor of 4 minus m, that's the same binomial. So now I'm going to factor out the 4 minus m. And what am I left with? 5 minus 3n. And if I wanted to check myself, which if I have time on an exam I will, then go ahead and FOIL, right? 4 times 5 for first is 20. Outer, 4 times negative 3n is negative 12n. Inner, negative m times 5, negative 5m. Last, negative m times negative 3n is positive 3mn. Right? So if I have time, I'm going to check myself. All right, so if I take a look at B, all right, if I take a look at B, okay, another factor, or I see another 4 terms, right? So I'm suspicious it might be factoring by grouping. And if I look at this, I don't see anything really in common to all 3. Like this just has P's, this just has Q's, so there's no GCF I can take out. So I'm gonna try first 2 and last 2 and see what happens. If it works, great. And if it doesn't, then that's okay too. I'll try a different combo. Right, so again, if first 2, last 2 don't work, I'll go first and third, second and fourth. And then if that doesn't work, I'll do first and fourth, second and third. All right, but the way I have it, it looks like I can take out a p here. And I'm left with p squared. Okay, if I take out the p, I've got minus 2q squared. All right, and so just right here, I can actually see I have a difference of squares. Right, I have p squared and then in parentheses root 2q squared. So I'm just gonna, my spidey senses go off when I have differences of squares. All right, let's look at the back 2. I have p squared q and 2q cubed, so I'm gonna take out the q, and I'm gonna have p squared minus 2q squared, right? There's that difference of squares again. Okay, so I've tried factoring by grouping, and then that checks out. So I'm gonna factor out the p squared minus 2q squared, and then I have what, p minus q left over. And now this here, right, my difference of squares. Remember, if we had a squared minus b squared, that was a minus b, a plus b. And so I just have to think about what is playing the role of a for this particular problem and what is playing the role of b. And a squared and p squared line right up, right? So a is being played by p. All right, and b squared is being played by the square root of 2 times q. Because if we think of the square root of 2 times q, and I square it, well, square root 2 times square root 2, right? If you think of root 2q times root 2q. Actually, let me not even write that with parentheses. I think it actually makes it a little bit more convoluted than it needs to be. Root 2q times root 2q. Well, square root of 2 times square root of 2 is 2, right? And q times q is q squared. So this is a difference of squares. Even though 2 doesn't seem like a perfect square, I can write it as, in parentheses, root 2 squared. So what I'm saying with all of this is for a minus b, I'm going to do p minus root 2q. A plus b is going to be plus p plus root 2q. And then let's not forget this p minus q on the back end. And now that these are all linear factors, then I know I'm prime. Okay. All right, so C is going to be the funkiest of all of them. This was the one that's going to hurt the most, so we'll spend some time on this. So you might initially think, oh, there's 4 terms here I can factor by grouping. And you can try, right? Make all the effort you want, right? You can try and group these first 2 and these last 2, right? But it's not going to work out the way you want, right? And then you might try the first and fourth and the second and third. It's still not going to work out the way you want. You won't get that back factor to match. And let me just show you real quick so you can see it, right? If I looked at 9x squared plus 24x, I'd factor out the 3x, right? And I would get 3x plus 8. Okay, great. 16 and y squared have nothing in common, right? So this back factor and this back factor don't match. This didn't work, which is fine, right? It's just a matter of recognizing it doesn't work. And then you might say, well, 16 minus y squared is a difference of squares. Agreed, it is, but it doesn't get you anywhere. All right, so what's really funky about this one, and this is gonna come with a lot of practice, right? This is the first time you're seeing something like this. These 3 together are a perfect square trinomial. All right, so I'm gonna put a little space here and I wanna talk about just 9x squared plus 24x plus 16, okay? And this would just come from practicing this a lot, right? And this is what I mean, like I see 9x squared and I'm like, well, that's 3x squared, right? And 16 is 4 squared. And anytime I see perfect squares like that, again, spidey senses go off, but it comes with experience. So the other thing I noticed is if I took 3x times 4, right? If you did 3x times 4, that's 12x. And this is double that. So where I'm going with this perfect square trinomial is ultimately 3x plus 4 quantity squared. Okay, and if you don't believe it, let me just play this out, right? 3x plus 4 times 3x plus 4. If we were to FOIL this, right? 3x times 3x is 9x squared, right? Outer, 3x times 4 is 12x. Inner, right? 4 times 3x, also 12x. Last, 4 times 4, 16. But these are like terms, so that does get me to 9x squared plus 24x plus 16. All right, so this all comes with experience. Anytime I see 9s and 16s, again, spidey senses go off because those are perfect squares. And then I did notice that 24x, right, is double that 3x and 4 multiplied together. So I'm like, oh, there's my perfect square trinomial. So what that means is this trinomial, I'm going to rewrite as 3x plus 4 squared minus y squared. And now I have a difference of squares, right? We're going to build on this. I told you this one's super convoluted and it hurts. All right, difference of squares. If we think about a squared minus b squared, right, which we know we can factor into a minus b, a plus b, my a this time out is 3x plus 4. So I'm going to put a 3x plus 4 here and a 3x plus 4 here, right? And my b is y. So I'm going to put a y here and a y here, right? So I'm not saying it's not convoluted. It absolutely is. But let me scooch this up so we can kind of complete this, all right? So I have a difference of squares, a squared minus b squared. So this is a minus b times a plus b, right? So this is my end game answer. And let's just say you wanted to check this, right? If you want to check it, which you would need to multiply that back out to check it, totally valid. This is a trinomial times a trinomial. So I want to talk about how you could check it, right? So if I wanted to check myself, all right, what you need to do is you need to distribute. You need to multiply the 3x to the 3x, the 4, and the y. Then you need to multiply the 4 to the 3x, the 4, and the y. And then you need to multiply the negative y to the 3x, to the 4, and to the y, right? So you got to do these 3 terms times these 3 terms. So it's ultimately 3x times 3x plus 4 plus y plus 4 times 3x plus 4 plus y minus y times 3x plus 4 plus y, right? And you can see if you were going to go backwards, right? These 3 terms have 3x plus 4 plus y in common, and I'm left with 3x plus 4 minus y, right? That does get me back there. Let's keep distributing. 3x times 3x, 9x squared. 3x times 4, 12x. 3x times y, 3xy. All right, 4 times 3x, 12x. 4 times 4, 16. 4 times y, 4y. Be careful distributing the negative. Negative y times 3x, negative 3xy. Negative y times 4, negative 4y. Negative y times y, negative y squared. All right, and I just want to see if I simplify this, do I get back to this original term? All right, let's take the x squareds. See 9x squared here. No other like terms. All right, let's do the x's. I got 12x, 12x, no other x terms. So I've got a 24x. All right, let's do the xy's. 3xy, right, minus 3xy. These cancel. Okay. All right, let's look at the constants. All right, if I look at it, I've got 16, no other constants, right? So let me go ahead and write plus 16. Next, I see this 4y, right? I got positive 4y and negative 4y. Those are going to cancel. And then last, I have minus y squared. So sure enough, when I did multiply this garbage, right, this hot mess, this trinomial times this trinomial, which is ultimately a difference of squares, I did get back to my original expression. It definitely hurt along the way, but I got back there. All right, thanks so much, everyone. Bye.